Sorry for those at home there. That should work now. Whoever was watching, the audio just kicked in. We're just reviewing here. Anyway, the selection sort algorithm that we developed here, if we wanted to sort an array of 1 million elements, that would have taken 20 minutes. If we went up to 10 million, it's going to take 100 times slower. 100 times slower, 100 times 20 minutes, that's a day and a half, right? So can we do better? Yes, and we introduced another algorithm, quicksort. And as the name suggested, it's much quicker. It's n log n comparisons. The analysis goes beyond the scope of this course, but we'll see it in action here. So everything that we've done up to this point, what I'm going to do is I'm going to throw it all away, because that's not what you do. You don't write your own sorting algorithms. You don't implement your own quicksort. You don't implement your own binary search. Instead, what you do is you use what's available in the standard library, right? And that's what we're going to focus on today. If you did end up rolling your own sorting algorithms, what would you end up doing? What would selection sort look like if we wanted to sort in, oops, let's go ahead and change this back to integers here. If we wanted to sort it in ascending order versus descending order, all we'd have to do is change which way we're comparing, right? Are we searching for the minimum and putting it at the beginning, or are we searching for the maximum and putting it at the beginning? What if we wanted to search books or sort books instead? That would be yet another implementation of selection sort, selection sort, selection sort. I don't want to have to deal with that, so I'm not even going to bother writing my own algorithms. Instead, which of course you don't want to do because it's just a lot of copy pasta, a lot of testing, a lot of debugging, you don't roll your own, right? Instead, you use what's built into the standard libraries. However, there's a catch. If you only have one sorting algorithm, that sorting algorithm has to work for integers, it has to work for doubles, it has to work for everything. So we have this kind of landscape right here. This generic sorting algorithm is responsible for sorting things. Oh, these two things are out of order. I'm going to go ahead and swap them so that they're in order, right? Or quicksort. I chose my my pivot element, and I need to put things that are less than it over here and things that are greater than it over here, right? In other words, I need to look at these two things and say, oh, this one is less, and so it goes over here, or this one is greater, and it goes over here. A sorting algorithm knows how to sort. It does not know how to order, though, right? Given A and B, does it go like this, or does it go like this, or does it go like this? Right? That's where a comparator comes in, right? This other component here. So the idea is that we give this sorting algorithm a generic array. It could be an array of doubles, it could be an array of integers, it could be an array of anything, right? As long as we give it a comparator for those things that follows this pattern over here that we'll talk about in a second, it can sort whatever you give it, and it'll output a sorted array, okay? What is the pattern? Well, given A and B, if A comes before B, it will return something negative. If A comes after B, in other words, they're out of order, then it returns something positive. Right? If they're the same, it returns 0. We've seen this before when we do string comparisons. strcmp has exactly this pattern here. In fact, every single programming language that you'll probably use in your entire lives follows this pattern, right, of a comparator. You don't write your own sorting algorithm in Python. You don't write your own sorting algorithm in C# or C++ or whatever. There are built-in sorting algorithms. What you do need to write, though, is orders for how to order code for how to order things. Does it go like this, or this? And that's where a comparator comes in. In the C programming language, that's called a comparator function. A comparator function has a very specific pattern and a very specific signature. All right, oops, sorry, there we go. So comparator functions. A comparator function is a function that compares two things. And I'm emphasizing, here, I'll super emphasize it. They are things, right? What are they? Are they integers? Are they doubles? Are they books, right? The answer to all of that is yes. It's whatever you want. They're just things, generic things, A and B. And returns. Again, that pattern. It returns something negative, something positive, or 0, depending on the relative ordering of those things. And I'm emphasizing the key word there, something, right? It could, when we write our own here, I'm just simply going to keep it simple and and return +1, -1, or 0. If you want to, you can return positive 42. I don't know why you'd want to. You could return negative 101, right? You can return whatever you want. Don't read anything into the magnitude of that number in general, right? I'm going to keep it simple with 1, 0, and negative 1. And so you should not read anything into the magnitude of the actual returned value here, right? In C, the signature of the function has to follow the following. Has to be the following. It returns an integer, right? The name is inconsequential. The name should be descriptive of what it does. But it takes these two things right here. Const void star A and const void star B. So does it take two integers? Nope. Does it take two doubles? Nope. Does it take two books? Nope. It takes two things. What is a thing in C? A void pointer, a void star, a generic void pointer. Where have we seen that before? Where have we seen this pattern? Void star. Malloc. Right? Is there a malloc for doubles and a malloc for integers and a malloc for books? No, there's one malloc, right? You just say, I want this certain number of bytes, and malloc gives you a chunk of memory. What you choose to do with that chunk of memory is your business. If I want to treat it as an integer, that's my choice. If I want to treat it as a double, that's my choice. It's generic, right? So that you only have one malloc. You don't have 50 different mallocs and have to rewrite malloc every time you need a new one, right? I'm not going to rewrite a quick sorting algorithm every time I need to sort something new. Instead, I'm going to keep it simple and keep it generic like this, right? So let's break that down into each of its components. It returns an integer, right? Following the pattern above. That is something negative, positive, or 0, depending on the relative ordering of it. It takes two arguments. Generic void pointers. Right? The const, that's, malloc doesn't return a const because it assumes that you're going to do something with the memory and change what's in the memory. But in this case, does a comparator need to change the things that you give it in order to compare them? No. So the const keyword ensures that no changes are made by the comparator function. Why is it there? That's a little bit better rendering. Okay, there we go. All right, inside the function, you follow a very general pattern, right? What we're going to do, and I'll document this after we do it, but you're going to want to cast it to the specific types that you are trying to compare, because if there's just this thing and this thing, the comparator is not going to be able to tell that it goes like this, this, or this, right? It needs to actually have some information about those two things in order to compare them. And then you follow the general pattern of returning something negative if this comes before this, something positive if it's out of order, or 0. Right? So for us, let's go ahead and take a look at, in fact, what I said is I'm going to throw away all this stuff, and I'm just literally going to do that now. Right? Tossed it all out. Why? Because there are better ways of doing it. Here I've got my array, and let's go ahead and get rid of all of this for now. There we go. And let's just focus on this, sorting this one integer array, okay? First, I need a comparator. I need a comparator for integers. Right? This is a comparator for integers that orders them in ... So now there are two ways that we can sort integers, right? We can sort them in ascending order, or opposite would be descending order. Which one do we want to do? Does it matter? No. Why? Because if we wanted to do the other way, what would we do? Write another function, right? So this comparator is for integers that orders them in, let's just go with ascending. Generally, ascending is the default in most programming languages. And then if you want a descending, you just reverse it, right? In ascending order, right? Note here the word I'm using. I'm not saying that it sorts them, right? It doesn't sort them. It orders things. It just orders two things. It goes like this, this, or they're equal, right? A sorting algorithm would be responsible for actually sorting them. So orders them in ascending order, right? So let me go ahead and write this function. It needs to return an integer. It needs to be a comparator. But here I'm going to be more descriptive in the name of the function. What is it comparing? It's comparing integers. So let's call it integer comparator. And let's also specify that it's in ascending order, ASC, short for ascending. If you want to write it all out, that's fine too. Right? I'll just go ahead and abbreviate it here. Right? Now, does it take two integers and order them, and orders those two integers? Is that a comparator? Doesn't look like it to me. A comparator is generic. All right, so change this to void star and void star. Is that a comparator? Careful, what else am I missing? Const. I'm making a promise here that I'm not going to change it. Here, by writing it like this, I'm breaking that promise and saying I'm probably going to change it, or I can change it, therefore you have to assume that I will. Const. Const. There we go. All right, so I've got A and B. Now, are A and B integers that I can do something like this with? If A is less than B, right, then I'll return -1. Something negative, because A comes before B. They're in order, right? Now, is that right? What are A and B right now? They're what? They're anything, right? All they are raw memory addresses. It's pointing to this memory address and it's pointing to this memory address. Does it make sense that this memory address, that this value comes before this value just because this memory address comes before this memory address? No, right? So we need to dereference them. Is that correct? I mean, now what I've done is I've jumped to that memory address and I've looked at what's in that memory address. But how does it know that it's an integer? An integer is 4 bytes, right? This integer is 4 bytes. If it knows that it's an integer, it can compare 4 bytes to 4 bytes. It's not necessarily an integer, though. It could be a double. And a double is 8 bytes and 8 bytes. How does it know to compare 4 bytes versus 8 bytes versus, say, a book, which is 40 bytes? It doesn't. So the first thing that I need to do is I need to make these into the types that they are, right? I will cast A and B as the types that we expect. Right? The types that we expect are integers. So const int star x is equal to const int star a. And I'll do the same thing for b. Right? I've changed them into x and y. A and b are just raw memory addresses. But now x and y are pointers to integers. Now I can do something with them. Now I can dereference them and look at that value and say it's 5, and then this value down here is 10, and 5 comes before 10 in ascending order, right? And now I can do something like this. Else, if A is greater than B, what should I return here? 1. It could be anything positive, 42, right? 101, right? Anything. Well, 0.5 is positive. Can I return 0.5? No, what's going to happen? Integer truncation, therefore 0. Are they equal? No, they just said that one's strictly greater than. Right? Don't do that. Only work in integers. Don't work in floating point numbers. Right? So return 1. Don't get fancy. 42, just to be different. No, just keep it simple. Right? Else, what's the only other possibility here? They're equal, so return 0. Now again, what am I doing here? I'm casting them as the types that they need to be. What if I passed in double pointers instead? Right? References to doubles. Well, that's on me, right? This is, in fact, I put it in the name. This is a comparator for integers that orders them in ascending order. What are you doing calling doubles on this function, right? You shouldn't be doing that. Just like if you called the square root function on a negative value. Right? Well, why'd you do that, right? You can do some rudimentary error handling, but ultimately that's on you, right? Don't call it with the wrong types. What am I doing here as far as something that we've seen before? Remember malloc. Malloc gives you a generic void pointer. What do you do with that generic void pointer? You typecast it to force it to become a string, a char star, or force it to become an array of integers, right? I'm doing the same thing here. I am forcing this generic void pointer to become an integer so that I can actually make some comparisons here. Okay? There's our first comparator. They're all going to follow that same basic pattern, right? that you are going to cast the generic void pointers as the actual types that you're comparing. And then you set up an if-else-if statement to return something negative, 0, or something positive, depending on the relative ordering of them. That's all you need to do. Once you've got your comparator, you can now sort. Right? Sorting in C, right? Sorting with qsort. There we go. It is an actual function in the standard library. Qsort, what do you think the Q stands for? Quick sort, right? It's quick. It doesn't necessarily have to be a quicksort implementation. Modern implementations are usually some modified merge sort or something like that, or some bottom-up merge sort like Tim sort, named for the guy that wrote it, Tim. Right? But anyway, it's still called qsort because that's what it was originally called. Right? So once you have a comparator function, you can call this standard library function qsort. Here's its signature. Right? It takes 4 arguments: base, NEL, size, and then this thing here, which is weird, and we're going to talk about that momentarily. Right? Does it return anything? Nope. Why? Just our selection sort didn't return anything, did it? Right? We gave it the array, it modified the array, rearranged it, and then returned. Right? It changed what you gave it. So quicksort doesn't do that either. Does it take an array of integers? Does it take an array of doubles? Does it take an array of books? No to all those questions, or yes to all those questions. It can. It can take any array of any type because it's a generic void pointer. Right? That's what base is. It's the array of elements. And again, I'm not going to give a name to those elements because it could be integers, it could be doubles, it could be anything, right? That you're going to sort. NEL is the number of elements in the array. We had to do that with quicksort, or we had to do that with our own selection sort too, right? Anytime that you're passing an array to a function, you also need to tell the function how big the array is. But what about those other things? What about size? Size is the number of bytes that each element takes in the array. Why would it need to know that? If it's going to swap 2 elements, and they're integers, an integer is 4 bytes, 4 bytes. If it's going to swap these 2 guys, it needs to know, I need to take these 4 bytes and put them into a temporary variable, take these 4 bytes and put them over here, take these 4 bytes and put them over here. If it's a double, right, it needs to know that it needs to take these 8 bytes and these 8 bytes and swap those around. If it's a book that's 40 bytes, it needs to take 40 bytes, and swap those around. So it needs to know those things. How do we tell it how many bytes are in the array, are in each element? Do you remember? How do we call malloc and say, I want 50 integers, 50 times use size of, right? Of whatever you're sorting, right? Presumably you called malloc to actually set up this array, so of course you're going to use size of again to tell qsort that how many bytes each one takes. Right? The last thing, more on this later, compare is a function pointer to your comparator. Right? More later. Comparator. There we go. Comparator. Right. I don't think that you'll find that in any dictionary. It's a computer science thing, right? We invent terminology, we invent new words as needed, right? It's a function pointer to your comparator. For now, just know that you use the function's name, okay? We'll understand that on Friday when we go through more details on function pointers. For now, I want you to get used to using qsort. So I'm going to replace, I've already deleted my selection sort here. Let's go ahead and get rid of that entirely. We're going to print the array, see it that it's unsorted. We're going to call qsort, print it out again to see that it's now successfully sorted. Right? Qsort. What are the things that I need to pass to it? The first thing is the array that you want sorted. The second thing is the number of elements in that array. That's exactly how we designed our selection sort. Here's the array, here's the number of elements in it. What about the second, or the third and the fourth arguments here? The third one is the things that the number of bytes that that each element takes that you're sorting. Well, what am I sorting here again? Integers. So how many bytes does an integer take? Do I hard code it to 4? Nope. What do I do? Size of int. There we go. Now this last one is the comparator that you want to use. The comparator that I want to use is this function right here. Order integers in ascending order for me. And so I'm going to pass it in like this. Right? It's just the function name. Don't confuse it with this. This is wrong right here. What I'm actually doing when you put parentheses on a function name, you are actually calling the function, invoking the function. That's not what I'm doing here. What I'm doing is I'm taking this function and I'm handing it off to another function. It's called a callback. Right? And we'll understand that a little bit better on Friday. For now, this is just how you use it. Okay? Let's go ahead and see if this works. Oops. Not A and B. What is it? X and Y. Oh, you guys didn't correct me. Right. X and Y. There we go. Compiler did. Thank you. Right. There we go. So don't be afraid to yell out when I make a mistake like that. Right. All right. So again, the values are 6492335, and we'll see this immediately if it actually sorts. Oh, awesome. Right. 2, 3, 3, 4, 5, 6, 9, 9. I didn't have to write any line of code here. I didn't have to write my own selection sort algorithm. I didn't have to write my own quick sort algorithm. I didn't have to write my own algorithm at all. Right? It was already built into the library, into the function, into the standard library, or into the language. All I had to write was this one component here that specified how to order things. Right? That's a comparator. Okay? Well, I've changed my mind. I don't want to sort them in ascending order anymore. I want to sort them in descending order. 9, 9, 6, 5, 4, 3, 3, 2. Right. What would I do with my comparator here? I'd have to change the name, and I'd have to change these things around. I don't want to do that. Let's go ahead and write another comparator, because sometimes maybe I do want to sort them in ascending order. Other times maybe I want to sort them in descending order. Right. Descending. Right. Descending. Right. There we go. I still typecast them. How do I change this so that I reverse the orders? If A is less than B, they're no longer in order anymore, right? 2 and 5. That was the order before, ascending. But now I want them to be descending, so they're out of order. What do I return now? 1. What do I return if they're in order? Because I've got 5 and 2. -1. Does 0 change? Nope. There's a good implementation. Is there a better way? Or is there an alternative way? I'll undo, undo. All I would have had to do is change these around. Greater than, less than. There we go. Is there an even better way? Remember that this one returns something negative, something positive, or 0. Right? If I want to flip those around, what could I do to the result? -1 becomes +1. +1 becomes -1. So what could I have done instead? Int result from this other one of A and B. And then I could say result is equal to result times -1. Right? I'm just, -1s become +1s. +1s become -1s. What about 0? Stays the same, right? And then return the result. So I cut maybe a dozen lines of code here down to 3. Can we go further? Can I cut those 3 lines down to 1? -1 times that. There we go. All right, great. I'm playing a game called Code Golf, if you've ever heard of it before, right? You need to implement something. I can do that in 10 lines of code. Oh, I can do that in 7 lines of code, right? Lower scores are better, just like in golf. I can do that in 4 lines. Well, I can do that in 4 lines and 3 fewer characters, right? You keep going like that. So help me out. Can we keep going like that? Do I actually need to multiply by -1? Nope. I could just negate that. Can you do it in 1 fewer characters? Don't multiply at all. Don't negate at all. Just flip them around. There we go. And that's it. Right? I don't think you can get any further than that. All right. Now let's go ahead and use that instead. Descending order. Right. GCC. Run this. And now it's 996543332. Cool. All right. Well, that's all great. That's great and all, but is it better than selection sort? Well, this works on 8 things, right? Could it work on, say, 1 million things? Let's go ahead and run our experiment again here and get a random array of size 1 million elements. Let's start small, like 10. And let's go ahead and quick sort it. It really doesn't matter, descending or ascending, right? And then let's print it out, just to make sure that it works, okay? GCC. There's a different random array, 83, 86, 77, 15, ... Oops, BRR. It didn't work because I didn't sort the correct array. There we go. So now this should be in descending order, whatever random values it comes up with. Oh, and I need to seed it, sorry. srand of time null. Right. And recompile that. Oops. I need to bring in the time library now because I'm using it. Time. There we go. There. Now let's run this and see if it works. 92, 87, 60, 59, all the way down to 8. Right. Is that in descending order? Good. Run it again. You'll get the same, not the same exact results, but you'll get the successful sorted in descending order results over and over and over again because some very smart people already wrote this Q-sort algorithm, and it's got 40, 50 years of debugging, optimization, testing, et cetera, right? I'm going to rely on a standard library function way more than something I've ever written, right? And everybody should. Now let's go ahead and get rid of the print statement here. And let's bump it up, 1,000. Right? Well, selection sort wasn't all that slow on 1,000 either, right? This one is immediate as well. In fact, let me printf done, right? I'm not actually going to print this out because I don't want to look at 1,000 things and see that they're all in descending order, right? So GCC, there we go. Done in a blink of an eye. 10,000. Oops. Done in a blink of an eye. Is that better than selection sort? Or when did we start seeing the performance degradation on selection sort? Do we remember? 100,000 or so? Okay. I think it was what, 12 seconds or so? Immediate. That's not 12 seconds, right? In fact, let's go ahead and time it. 0.02 seconds. Right? Now, if I go up to 1 million, right, remember it was going to take 20 minutes for our selection sort algorithm. What do you think it's going to take now? Well, remember it was quicksort was quasi-linear. If I go up by a magnitude of 10, we would expect a performance degradation of a magnitude of 10. Right? In other words, it was taking 0.02 seconds. It's probably going to take what? 0.2 seconds now. Right? That matches our theoretical analysis that we did on Monday. Of here it is, its performance is n log n. So if you go up by a factor of 10, you can expect a slightly greater than, but basically it's going to be 10 times slower. Well, what about 10 million? Right? Now, if we were still on selection sort, that would be 100 times slower. 100 times 20 minutes is, I think, 33 hours. Right? Versus this. It's going to be 10 times slower. 10 times slower than 0.2 seconds is 2 seconds. 2.4 seconds or so. Right? Just slightly a little more. So 33 hours, a day and a half versus 2 seconds. Is there any contest whatsoever there? Right? No. Right? It's not exponentially faster, it's polynomially faster, but it's a huge speed up. Right? If we went up another order of magnitude here, I'm not going to do it, but what would it take here? About 25 seconds or so, maybe 30 seconds. But what would it take for selection sort? 100 times 33 hours is going to be Wolfram Alpha. 3,300 hours, 2 days. Okay, yeah. Well, let's say months instead then. Yeah, 4.5 months versus, what did I say? 20 seconds or 30 seconds, right? Now the gap becomes bigger and bigger and bigger as you go out to infinity, as the array sizes grow and grow and grow. Right? There is no contest here. Right? Well, we can go ahead and sort in C now. What about searching in C? Right? There's a binary search implementation called bsearch. Okay? It looks very, very much like quicksort over here. It takes a base, number of elements, NEL is short for number of elements, a size, and this comparator function here. But it also takes a key. Another thing that's different is its return value. Up here, quicksort returned void. Why? Because it wasn't going to give you anything back. But if you're searching for a needle in a haystack, you'd better expect something back. I found it. Here you go. Here it is. Right? And here's the key that you're searching for. Once the key matches an element, it gives you that element back as a generic pointer. Why? Because we don't want to binary search for integers. We don't want to binary search for doubles. We don't want to binary search for books. We want a binary search that operates generically on any type. Right? And it will operate generically on any type. Here's the array. Uh-oh, there's another difference. Over here and with quicksort, we were going to make changes to the array because we were going to rearrange it. Are we making changes if we're just searching the array? Nope. So we made a promise here that we're not going to change it. Again, what's the behavior here? It returns a pointer to a matching element, or an element matching the given key element. And note here, I'm going to really emphasize on element because there could be more than one. Right? If you're searching for 5 in an array and there are 3 of them, which one does it return? Who cares, right? It returns one of them. Right? If no such element is found, it returns, guess what? Null. Why? Because it returns a pointer. What's the only pointer that makes sense for an error, for I did not find it, et cetera, et cetera? It returns null. Right? bsearch makes no changes to the array, thus the const keyword. Right? The first argument is a dummy key that you are searching for. Right? More on that here as we get to more complex comparators or comparisons. Okay, but first let's go ahead and see how to use it over here. Okay, I'm going to go ahead and get rid of this benchmarking stuff. All right, we've got our array. We sort it in descending order, and I'm going to print it out, make sure that it's still sorted. Now I want to search for it. Right? Our old binary search here gave you back the index. bsearch, however, does not. bsearch gives you a pointer to the element. Int, I don't know, needle? There we go. And it's going to return a pointer. We're going to search our haystack for a needle. The arguments that we give it are going to match exactly the same 4 arguments here, except for the first one. The first one needs to be a key of what we're searching for. So in this case, int key is equal to, let's go ahead and search for 42. Right? 42 will be an unsuccessful search here because it's not in there. Right? All right, and I'm going to pass in a pointer to it. Why did I put that ampersand in front of the key? What does bsearch require or expect? A pointer. What is key? Is it a pointer? Nope, it's a regular old variable. So how do I take a regular old variable and change it into a pointer? By putting an ampersand in front of it. Right? Otherwise, it's going to be exactly the same. Array, the number of elements in the array, the number of bytes that each element takes, and then cmp int desc. There we go. Now, if the result is, if the search is unsuccessful, it will return null. Let's check for that. If needle is null, then we'll print f did not find key value %d and line key. Right? Otherwise, if it's not null, then we have successfully found it. Printf success found %d and the line. In this case, though, I'm going to dereference needle. there we go, at memory location %p. If I don't dereference it, remember that that is the memory address of that thing. Okay? All right. So what should it print here? I don't need to time it anymore. Are we going to find 42 in that array? Nope. Did not find the key value 42. All right. Let's change the key to something that is in there. Say 9. Okay. Is 9 going to be in there? Yeah. Which one was it? I don't know. Right. One or the other, right? Does it matter? Right? No, binary search is just there to return a value that matches the key. If you wanted all of them, you're shopping for a different algorithm, right? It might have found this one, it might have found this one, in which case you would probe left, you'd probe right to find them all, right? Tell me what's going to happen here. Ascending. Yeah, like this. GCC. All right. So I'm going to sort it in descending order, right? 987654321. But I'm going to search it using the comparator that assumes that it's in ascending order. Is this going to be successful searching for 9? Let's find out. Did not find the key value 9. It's right there. Why didn't it find it? Remember how binary search works. It looks in the middle, right? That's not the thing I'm looking for. Let's suppose that the middle here is 4. I'm searching for 9. Using this comparator here that assumes that it's in ascending order, where would you assume that 9 is? In this half of the list. Is it? Nope. So the key takeaway here is, if you're going to search using binary search, you have to use the exact same criteria, right? You can't use two different comparators, right? That go in different orders, okay? Now it will be successful because I'm being consistent about it. Found it at memory address, whatever. Right? Cool. All right. Let's get more complicated. Remember the book demo? Right? The book demo, we load up a bunch of books from a CSV file that looks kind of like this, right? So we've got Harry Potter, we've got Game of Thrones, et cetera, right? And we ran several reports on it. We found the best book with respect to the ratings. We found the worst book with respect to the ratings. And then we reported them both. Let's focus on those two first. How could I use searching and sorting to solve this problem rather than writing my own algorithms for it? What if I sorted the books by rating? If I sorted them by rating, what would be at the top? The best book. What would be at the bottom? The worst book. If I sorted them in descending order. If I sorted them in ascending order, right, 0s to 5s, then where would the best book be? Down here. Worst book is up here. Let's do that. Let's write a comparator to sort books by, or to order books, excuse me, by their rating in descending, ascending order. It doesn't really matter, right? So comparator for book structures that orders them by rating in ascending order, descending, which one? Descending? Okay. Descending order. Right. There. All right, well, if it's for books, then I should call it CMP books by rating. Right? Compare books by rating. And I should take two books, book A and book B. Is that a comparator? Nope. It is only a comparator if and only if it follows this signature right here. Right? That begs the question, what does strcmp look like? strcmp. Does it take two const void pointers? Sorry, right there. Nope. Is it technically a comparator? Nope. You would not be able to use this to sort an array of, directly at least, to sort an array of strings. Right? You'd have to do so. You could use it as part of your comparator, but you couldn't use it in general. All right? So it has to follow that pattern. Const void star A and const void star B. Right. That's a comparator. Now let's come over here to our source file and let's implement it. What's the first thing that I need to do? Do I have any information about what A and B are? Like, can I access their ratings? Could I go say if A's ratings is less than B's ratings, then do something? Do I have enough information about what A and B are in order to do this? Not yet. The first thing I do is what? Typecast. Const book star X is equal to const book star A, and const book star Y is a typecast of B. Right? Now I do have enough information about them. They're now books, right? If they weren't books before, then this is going to be some segmentation fault or something, and then it's on me, right? There's no way to check to see that somebody actually gave you books, right? We're going to force them to become books, and if they ain't, then we're just going to let it seg fault out, right? There's no possible error checking here, right? The only error checking that you could do would be checking for nulls. If A is null or B is null, right? What do you do in this case, right? It depends, right? That brings up the question of, well, if I've got book A, book B, book C, but then I've got a null pointer, where does it go? It doesn't make much sense. Do you put all the nulls first, all the nulls last, right? I'm not even going to go there. So don't worry about it. Just let it die with a seg fault. Right? Okay. I've got my two books. How do I compare their ratings? X and Y are now structures, right? Regular old structures so that I can use a dot. Is that correct? They're not regular old structures. What are they? Pointers to structures. What do you use when you have a pointer to a structure? Arrow. If X's rating is less than Y's rating, right, and here's where I always confuse myself because which way do they go again? In ascending order? What was it? Descending order. Right. So note to self, descending. Right. 5 before 2. All right. So are they in order? Well, they're in order if that first one is greater than 2. And so what should I return now? 1 would be out of order, right? So the way that I always remember this is the number line. Negatives are over here. Positives are over here. Are they in order, or are they on the different sides of the y-axis, right? And so that's how I always end up remembering it, right? Left to right, -1. Else if X's rating is less than Y's rating, then I'll return +1. Right? There we go. Oh, thank you. There we go. I like to go in order. Right? I want to check greater than, equal to, or less than, then equal to, then greater than. Right? What's the problem with doing this with floating point numbers? Take 1 and divide it by 3. What do you get? In computers, you don't get 1/3. You get 0.33333. Now multiply that by 3. Do you get 1 back? In the math world, you do. But in computers, you get what? 0.99999. It's not equal to 1. Right? Don't rely on equality. Right? You didn't rely on equality when you were doing your unit testing for hack 5 or 6 or whatever it was, right? Where you compute some number like the Lorentz time dilation or something. And as long as it's close enough, you're good, right? If it's 0.00012 versus 0.00012000001, right? That's close enough. Right? Don't get into that quagmire of floating point errors and round off errors and estimations. It's close enough, right? Just go ahead and always generally have the equality condition as the last one. That's the pattern I follow. Right? So greater than, less than, 1, and 0. That all looks good. Remember, that's going to be in descent. Wait, which one did we say? in descending order. Is that what you suggested, or did you say ascending? Okay, all right. We're going to stick with this now. I don't want to change it. All right. Sorry about that. Misheard you. Or I just flipped it around in my mind, right? All right, so here's print each book. Before I print each book, let's go ahead and sort it by rating. Q sort. Right? What's the first thing I give to Q sort? The array that you want to sort, that's library, my library books. How many things are in there? Num books. How many bytes does a book take? 4? 8? I have no idea. What does know? Size of book. Right, there we go. And then what comparator do you want to use? The comparator that I made over here. There. Now let's compile all this together. Book.c and book demo. Hopefully it compiles. Yep, it does. Don't worry about those warnings. Right. Oops. All right, run it. Oh, wow. It's really freaking out. There you go. Hopefully it'll still run at least. Oh, yeah, a segmentation fault here because we're not done. But it was at least able to print these out. Harry Potter and the Deathly Hallows, 4.62, all the way down to the worst book is Diagonetics, right? At 2.33. Right? All look good? So now what we can do to solve this problem that we had to write our own functions for before is don't call your own functions. The best book is where? At the top. Library sub 0. And because it expects a pointer here, I'm going to have to put an ampersand in front of it. Down here, library. Where's the worst book? At the end. Num books. Is that correct? If there are 5 books, is the fifth one at the end? 0, 1, 2, 3, 4. I need to subtract 1 because of 0 indexing. GCC. Run this again. And there's the list above. The best book is Harry Potter. Worst book is Dianetics. Right. How much time? Oh, we don't have enough time, so I'll have to continue it on Thursday or on Friday. But how do you go about searching for Frank's books now? Right? You don't write your own get book by author. Instead, you use binary search.